Hello and welcome to week 11 of NPTEL live session on the course of Foundations of Cryptography. So, to start with, we will discuss last week questions. Those are posted on NPTEL website. Let me proceed. So, first question in the assignment was, given the following statements, select the correct options below. Ilgammal encryption scheme does not have the malleability property. This is not correct actually. Ilgammal encryption scheme has the malleability property. So if you remember that in Ilgammal encryption scheme, the public key contains the group description. So basically some prime order cyclic group, right? Say capital G, and we also have the generator of the group and the size of the group Q. So generator we denote by small g and size of the group by Q. So all these informations are publicly available, and apart from that, there is another public key available, which is we denote it by H, and H is G to the power X, where X is the secret key. Okay, so X belonging to ZQ is the secret key, and G to the power X, which we denote as H, is publicly available. Now, for encrypting some message M, basically, so your ciphertext has the structure of C1, C2, right? So your C1 will be some H to the power, some G to the power R for random element R, and your C2 will be this H to the power the message element, right? Now, according to this malleability property, if you just multiply some element M dash to the second component of your ciphertext, basically, so it will give you the ciphertext corresponding to message M into M0, and because you know the value of original message, so you can because you know the value of M dash that you multiply with the second component of the ciphertext, you can compute its multiplicative inverse in the group as well, and using that you can basically recover what is the original plain text message encrypted in the ciphertext, right? So basically, using that malleability property only, you can break the security of Ilgammal encryption scheme. So it is Ilgammal encryption scheme is malleable, and that's why the CCA security of Ilgammal encryption scheme is also not there. Ilgammal encryption just gives us CPA security, right? By adding the randomness R. Okay. So the next option says that the hardness of CDH may not be the same as the hardness of DTH. So computational diffie-Hellman problem can be hard even if DTH is not hard. So basically there exists some group where even after an adversary gets access to the DTH solver, or in other words, even if DTH problem becomes solvable in that particular group, the CDH assumption still holds true. So the CDH problem still remains hard. Okay, so that's where comes the context of gap CDH problem, right? So basically the hardness of CDH is not same as hardness of DTH problem, right? So second option is correct. Third option says gap CDH assumption says that computing G to the power XY is not possible even in presence of a DTH solver, where G, A, B belonging to ZP star, and P is a suitably large prime, and A equal to G to the power X and B equal to G to the power Y. So basically the same statement is like the option, the statement 2 and statement 3 are basically same. So what CDH assumption says is that if you are given an adversary is given A comma B, where A is G to the power X and B is G to the power Y. Of course, X and Y are not known to adversary, but adversary is provided with the value of A and B only, and adversary has to come up with the correct value of G to the power XY. And that is what CDH problem says. And DDH problem says that given A comma B to the adversary, also if adversary is provided with triplet like A comma B comma C, where C is G to the power Y for some G to the power Z for some random value Z belonging to ZQ, then this triplet A comma B comma C should not be distinguishable from A comma B comma G to the power XY. So that is what DDH problem says. Now, even if the adversary has access to DDH solver, which can effectively distinguish between these two kind of triplets, then also the adversary should not be able to come up with the exact value of G to the power XY, which is the CDH problem. So computing G to the power XY is indeed not possible even with the access to DDH solver. So statement 3 is correct. Statement 4 says there exists some public key encryption scheme that is malleable and CCA secure. This is not true, because any encryption scheme you consider which is malleable, then to break its CCA security, what an adversary can simply do is that it can see the challenge ciphertext, right? And after seeing the challenge ciphertext, it basically just tweaks the challenge ciphertext in such a way that with that changed ciphertext queried to the decryption oracle, it can see corresponding plain text, which is some M dash, and M dash will be related to the actual plain text M, which is encrypted under challenge ciphertext. So by using the decryption oracle access and by exploiting the ciphertext malleability property, an adversary can be able to exactly say what is the underlying plain text of challenge ciphertext. So thus CCA security can be broken. So basically, whenever some encryption scheme is malleable, then it cannot satisfy CCA security. So fourth statement is wrong. Basically, among the given options, option 1 and 4 are incorrect. Proceeding to the next problem. Choose the correct options. Identification scheme in the public key setting consists of 3 algorithms. So this is wrong, because as you know, identification scheme actually consists of 4 algorithms. So there are one prover and one verifier in the identification scheme. What identification scheme basically does is that in many real world scenario, there are you may think of clients who wants to authenticate themselves to some server. So basically, that is where identification comes into play, that the prover is trying to prove that it is indeed a valid user to some service. Okay, so identification scheme has actually 4 algorithms. Those are, one is keygen, that generates one public key, which is also verification key available to any verifier in the public. So verification key is public, and there is one secret key SK. And apart from keygen, there are two algorithms which are used by the prover. We denote it as P1 and P2. And the verifier's algorithm, we denote it as V. So keygen, P1, P2, and V. These four are the algorithms used in identification scheme. So first option is incorrect. Second option says in a 3-round identification scheme, the prover's commitment and response are received by the verifier. This is also true. So what do we mean by 3-round identification scheme is that we have 3 round, first commit, then challenge, and then response. So first interaction, which is the commitment, basically goes from the prover to the verifier. So using the algorithm P1, right? Using the algorithm P1, a prover basically computes with the help of its secret key and some random value. It computes some commitment and sends it to the verifier. Now verifier comes up with some challenge, and the challenge space basically is parameterized by the verification key VK. Okay, so the challenger or the verifier comes up with some uniformly random challenge from the challenge set and sends it to the prover. So the challenge goes from verifier to prover. Now prover's job is to generate the response using the algorithm P2 and the secret key SK and the challenge say R. And whatever response it gets from the as output of the algorithm P2, we denote it as S, and this response S is sent from prover to verifier. So among the 3 rounds, the commitment and the response goes from prover to verifier, and in between the challenge comes from verifier to prover, right? And at the last, verifier's job is to basically verify whether this S is indeed a correct response corresponding to the challenge R. So it runs the verification algorithm V by taking input the verification key VK and R and S. As output, it is expected to get the commitment. So whatever commitment was sent from the prover to verifier in the initial stage, that same commitment is expected to be computed by the verification algorithm. If it matches, then verifier basically accepts that prover is indeed the entity who it claims to be. Otherwise, it aborts. So that is how identification scheme works. Now, so basically, second statement is correct. In the third statement, it says in the no message attack, just the public key is not enough to generate a forgery. So if you remember, in the context of RSA algorithm, we discussed no message attack. What it does basically is instead of calculating signature corresponding to some message in forward direction, it comes from the signature space to message space in backward direction using the publicly available verification key, right? So there are two keys, signing key and verification key in the context of digital signature scheme, right? Now, using the publicly available verification key, an adversary can basically choose some random signature from the signature space and then apply sigma to the power vk modulo n to compute its corresponding message. Okay, and now m comma sigma becomes a valid signature. So this is indeed a forgery. So public key is enough to generate a forgery. So third statement is wrong. Fourth statement says that an arbitrary forging attack which requires an honest party to sign random messages is unrealistic and is possible only in theory. So this is also again wrong, because if you remember, in an arbitrary forgery attack, with the access to signing oracle, an adversary is indeed able to come up with a valid signature corresponding to any given message M. How? Basically, it exploits the malleable property of naive RSA algorithm. So there, if you are given some message M and you are required to compute a corresponding valid signature sigma corresponding to M, then what you can do is that you can just come up with some message M1 from the message space, and by accessing the signing oracle, you can see the corresponding signature sigma 1. Okay, so sigma 1 is a valid signature corresponding to M1 that you get from the signing oracle. Now you compute the value of M into M1 inverse, and let's denote it as M2. So M2 is M into M1 inverse. And what does that mean is that basically it means that M1 into M2 is equal to M actually. So now that you have computed the value of M2 by doing M into M1 inverse, you access the signing oracle with the query M2 and you get to see the signature sigma 2 corresponding to M2. So you now know signature sigma 1 corresponding to M1 and signature sigma 2 corresponding to M2. Now you perform sigma 1 into sigma 2, which basically gives you a valid signature corresponding to M1 M2, which is nothing but M. So that is how you can generate a valid signature corresponding to any given message M by using the signing access oracle. This will be an arbitrary forging attack, which is indeed possible. So the fourth statement is wrong because it says that the attack is unrealistic. So our among the given option, basically only the second statement is correct. Okay. Next question, consider the following security experiment against the textbook RSA signature. The PPT adversary is given the public verification key VK and a message M from the message space by the verifier. The challenge for the adversary is to then come up with a valid signature on M without getting the signing oracle access at all. Then there are given some statements about whether the winning probability of adversary is somehow related to the RSA assumption. Okay. Now, just now what we discussed in arbitrary forging attack is that with the access to signing oracle, an adversary is indeed come up with a valid signature on M, that is arbitrary forging attack. But here it is saying that the adversary does not have the signing oracle access. Now, what is the winning probability of adversary and how is it related to the RSA assumption? Now, remember that RSA assumption basically talks about whether seeing a signature generated by naive RSA algorithm, you can actually tell what the underlying message of that signature is. So you have some message M and you are seeing M to the power VK mod N, sorry, M to the power SK mod N, right, which is the signature corresponding to message M. Now, seeing this signature, whether an adversary can tell the underlying message M or not, that is what RSA assumption. Now, that is what RSA problem is, and RSA assumption says that this is hard basically to come up with the correct underlying message M. Now, but what the adversary is required to do in this question is it is given some M and it has to compute sigma. So basically these two things are unrelated. Here adversary has been given some M and it has to come up with the corresponding sigma. But RSA assumption tells that given sigma, it is hard to compute M. So these two are basically unrelated. Whether the adversary will be able to compute the sigma corresponding to M here even without access to signing oracle, that is completely something different context from the RSA assumption. So our correct option is basically the last statement, which says the probability of the adversary winning the experiment cannot be related to the hardness of the RSA problem. Okay. Proceed to the next question. which of the following statements is or are correct? Any identification scheme can be used to get a signature scheme. So this is true. Basically, using fiat semi transformation, you can able to transform any identification scheme to a signature scheme. Identification scheme is basically interactive scheme, right? Where a prover tries to prove itself as a valid entity, okay, by interacting with the verifier, by generating valid response in reply to challenge selected by the verifier. But in case of signature scheme, actually, this interaction phase is not there. So you turn a interactive protocol to a non-interactive one by using the fiat semi transform. In signature scheme, basically, you need to do again some kind of authentication. So the signer wants to ensure that whatever signature it is providing with the message, it should be generated by authenticated signer only. And verifier wants to verify that the sign was indeed generated by some authenticated signer, right? But the protocol should be non-interactive. Okay, once the signature is generated, it need not the signer need not communicate with the verifier, and verifier can be anyone, right? So anyway, using the fiat semi transformation, it is possible to convert any identification scheme to a signature scheme. Second statement says that any encryption scheme cannot be used to get an identification scheme. This is true. Basically, the purpose of encryption scheme and identification scheme are completely different. Encryption scheme deals with confidentiality of data, whereas identification scheme deals with authentication of some entity. So we cannot generally say that any encryption scheme can be used to get an encryption identification scheme. So is this statement is correct? Public key identification schemes provide security against malicious adversaries too. This is also true because in identification scheme, if any malicious adversary, basically who is an imposter, tries to prove itself as a valid entity in the game between prover and verifier, so the malicious adversary does not have access to the secret key, but yet it tries to participate in the game and tries to generate valid response to a challenge chosen by the verifier. But it is not actually possible for the adversary to do so, which is ensured by the security of identification scheme. So identification scheme provides security against malicious adversaries. Fourth statement says CCA secure hybrid ciphers based on Diffie-Hellman problems require only DDH assumption to be true. But you have already seen that in CCA secure hybrid ciphers, we actually combine a CCA secure KEM and a public key encryption scheme in order to get a CCA secure hybrid cipher, and it actually needs the gap CDH problem to be true in order to be secure. So it does not require the DDH assumption to be true. Even if DDH assumption does not hold, that is DDH problem is easy to solve in that space, still gap CDH problem, if it is hard, then we can rely on CCA security of the hybrid ciphers. So fourth statement is wrong. Basically, first three statements are correct here. We want to build a variant of OTP based on multiplication modulo A prime P, where M equal to K equal to C, and encryption of M with respect to key K is expressed as M into K mod P, and decryption of ciphertext with respect to key K is noted as C into K inverse mod P, where K inverse is the multiplicative inverse of K modulo P. Select the correct statements. The scheme is not perfectly secure for ZP. Well, so ZP is not a multiplicative group, right? ZP has 0 as one of its element, and 0 is not invertible. But in multiplication group with multiplicative identity 1, uh, each element should be invertible, right? In order to satisfy the criteria of a group. So ZP is not a multiplicative group. So you cannot come up with 0, inverse of 0. So we cannot apply this kind of encryption decryption algorithm on a group ZP. But when we talk about ZP star, because P is prime, so ZP star basically consists of all the elements 1 to P minus 1, right? So all the elements that are co-prime to P, and except 0, because P is a prime number, except 0, all the element 1 to P minus 1 are indeed co-prime to P. So all of them are member of ZP star, and all of them are invertible as well, because the condition for a group element being invertible is that that group element should be co-prime to the to this modulus P, right? So basically all the elements are invertible here, and so this kind of encryption and decryption algorithm will work. And coming to security, whenever you see some random ciphertext C, so it can be generated in various ways. So corresponding to each possible key K, K can be element of ZP star, right? Because message space, key space, and ciphertext space are same, and all are ZP star. So K can be any of the any one of the P minus 1 element of ZP star, and for each such value of key K, there can be one possible value of the underlying message M as well, such that M into K mod P equal to C is satisfied. So basically, there is possibility that when an adversary sees the ciphertext C, the underlying message could be any one of the elements 1 to P minus 1, with each occurring with equal probability for various possible values of K. So because you cannot gain any extra information about the underlying plain text while seeing the ciphertext, we say that the scheme satisfies perfect secrecy. So the scheme is actually perfectly secure for ZP star. Okay. So here correct statement is actually the scheme is not perfectly secure for ZP. That is the correct option here. Okay. So entering into this week's topics. First problem, for Shamir secret sharing scheme, the correctness holds if the Lagrange's interpolation is performed over a ring. So basically, for this should be true for the algebraic structure field, because in field, all the elements except the 0 element are invertible. That is how the algebraic structure field is defined. Whereas in case of ring, a ring can be a field or it may not be a field, right? Because in ring, uh, all the elements of the ring except 0 need not be invertible. But in case of field, it is all the elements are actually invertible. But if you see the construction of Lagrange coefficients, there during Lagrange interpolation method, we actually multiply the secret shares of each of the participating T number of parties during recombination phase. We multiply the secret shares with the Lagrange coefficient. And in Lagrange coefficient, there is numerator and denominator, and whatever element is present there in the denominator, we basically need to calculate the multiplicative inverse of that element in the field F. Okay. So we need all the elements of that set to be invertible in order to get the Lagrange's interpolation work. So the correctness of Samir secret sharing scheme, that is by correctness of a secret sharing scheme, what we mean by that is let's say you have a T out of N secret sharing scheme, right? So each of the N parties has some individual shares with it, and any T of them when combines uh, with their individual T number of key shares, they should be correctly combined into the original secret S. So they should be able to reconstruct the secret S. And if they are able to reconstruct correctly, then we say that the correctness holds for that secret sharing scheme. And with the help of Lagrange's interpolation method performed over a field, the correctness of Samir's secret sharing scheme indeed holds. So first two statements are wrong. Third statement says that the privacy does not hold if the secret is said to be any other coefficient of the sharing polynomial except the constant term. So by convention in the Samir secret sharing scheme, the T degree polynomial that we take, we fix its constant term to be the secret. But that does not mean that if we initialize any other coefficient of the polynomial to be the secret, not the constant term, then also, of course, the scheme will work. And after reconstructing the polynomial using Lagrange's interpolation method, we can just extract that particular coefficient of the polynomial as our reconstructed secret. So it need not be positioned as the constant term of the polynomial only. That is not a requirement. But for the ease of computation, we fix the secret as the constant term of the polynomial, but that is not a necessity for the correctness of the scheme. So third statement is wrong. So none of the above statements are correct. So, okay. Now, next question. Which of the following is or are true for additive secret sharing? Let's look at the options basically. So the shares of up to n-1 parties need not be communicated if the adversary is computationally bounded and if there is a pre-shared uniformly random and private key between the dealer and every shareholder. Next statement says, irrespective of the kind of setup available, the shares of every shareholder have to be communicated even if the adversary is computationally bounded. Third statement says the shares of any party need not be communicated if the adversary is computationally bounded and if there is a pre-shared uniformly random and private PRF key available between the dealer and every shareholder. So if you would like to answer, you can unmute yourself and say. I will pause for a minute. You can think and come up with the answer. You can type in the message as well in the chat. Okay. So basically, the statement, the first statement, so it says that the shares of up to n-1 parties need not be communicated. So in case of additive secret sharing, what is basically additive secret sharing? So you have some secret S and you from the secret space, let's say the secret space is some capital K. So what you do is that you, for first n-1 parties, if you have total n number of parties, okay, among which you need to share the secret. In case of additive secret sharing, each of your party P1 to Pn minus 1, first n minus 1 number of parties, each of them are provided with some uniformly randomly chosen secret shares Si belonging to the key space K. Okay. So after n minus 1 such secret shares are generated uniformly randomly from the key space K, then the last share Sn corresponding to the party Pn is computed as the original secret S minus summation of all the SIs for I equal to 1 to n minus 1. Okay, that is how the last secret share Sn is computed. Now, although it may seem that Sn is dependent upon the value of the original secret S, but by information theoretically secure argument, you can say that first n minus 1 party's secrets are generated uniformly randomly from the key K, so they all are independent of each other, and even the last share Sn is also not dependent upon the original secret S actually. Okay. So basically the secrecy of secret sharing scheme indeed is retained even if the first n minus 1 party's secret are basically not shared by the dealer explicitly. So you can think of such scenario in multi-party computation where each of the party has its own share of input and they want to compute on their share of input without revealing their inputs. Okay. Basically, each of them then come up with its own share of secret. Okay. And after their computation is done with the help of some private PRF key, which is shared between the dealer and the first n minus 1 parties, the dealer can actually easily compute what should be the nth secret share. So the first n minus 1 number of shares need not be explicitly communicated by the dealer. It can be uniformly randomly chosen by the parties itself, and still the nth secret share can be computed by the dealer itself, and necessary computation goes on. Okay. So that is why it says that n minus 1 parties need not be share of n minus 1 parties need not be communicated, but depending on their value, the last share can be computed by dealer itself. This Zoom meeting ends in 10 minutes. So after it ends, the link to join will be sent in the same Zoom meeting. Coming to the second statement. So first statement is true. Okay. Second statement says irrespective of the kind of setup available, the shares of every shareholder have to be communicated even if the adversary is computationally bounded. This is wrong because just now we said that not explicitly all the n shares needs to be communicated to the shareholders. Okay, the shareholder can come up with its own choice of secret share, and the last nth party share can be computed accordingly. Okay. Third statement says the shares of any party need not be communicated if the adversary is computationally bounded and if there is a pre-shared uniformly random and private PRF key between the dealer and every shareholder. So this is essentially wrong because just in the first statement only we said that shares of up to n minus 1 parties need not be communicated. Okay. So so that is it. Only first statement is correct here. In the next problem, so consider the following variant of additive secret sharing. For sharing a n-bit secret among n shareholders P1 to Pn, where up to n minus 1 shareholders could be corrupt. to share an n-bit secret S equal to S1 to Sn, where S1 to Sn are the bits of the secret S. The dealer gives party Pi the share Si. So you have this secret with n number of bits and you want to share the secret among n number of parties only, and you provide each bit of the secret S as the corresponding secret share to party Pi. So Si is secret share of party Pi. So what happens is that basically you whenever, let's say, n minus 1 number of parties collude, so n minus 1 number of bits of the original secret is already known. It is only left to decide what is the last bit of the secret. Okay, and that last bit can be either 0 or 1. So always there is a probability of half with which this n minus number of set of parties, they can actually come up with the correct secret S. Okay, so this is not essentially a secure secret sharing scheme. So the options given are: the scheme provides perfect security, the scheme provides computational security, the scheme is secure provided n is sufficiently large. So whatever be the value of n, actually, provided n minus 1 number of bits are known, the last bit can always be determined with probability half. Okay, so none of the statements here are correct. Okay. So let's proceed to the next problem. It says, for the additive secret sharing scheme, the operations have to be necessarily performed over a ring. The operations have to be necessarily performed over a field. The privacy holds against a computationally unbounded adversary. The privacy property is guaranteed only if the adversary is computationally bounded. If you would like to answer, I will pause for a minute and you can answer. What about the first two statements? For additive secret sharing scheme, do we need the key space structure to be necessarily something or field or something? So basically, in additive secret sharing scheme, you just need the addition operation to be supported in your key space, right? Whatever algebraic structure you take. So essentially, for ring and field, both of them support additive kind of operation, even group also. So it is not restricted to ring and field only. So there is no such restriction that operations have to be necessarily performed over ring or field. Additive secret sharing can work over a group also. Okay, additive group. So anyway, first two statements are wrong. Third statement says the privacy holds against a computationally unbounded adversary. This is also true because in additive secret sharing scheme, when n minus 1 number of parties collude, so you have the summation of all the SIs for I belonging to 1 to n minus 1, and they try to come up with a valid guess for the share Sn, the nth share. But because all the n minus 1 shares are completely independently chosen random element from the key space, they cannot at all leak any information about the secret share Sn. The only option is to do the random guess, which has the probability of being correct of 1 by 2 to the power n, where n is the bit length of the secret. Okay. So basically, with probability 1 by 2 to the power n, which is negligible, even with any unbounded computation power, the adversary cannot be able to correctly come up with the nth secret share by seeing the n minus 1 number of secret shares. So that is it, that even with unbounded computational power, the adversary should not be able to guess the nth secret share except with negligible probability. The last statement says the privacy property is guaranteed only if the adversary is computationally bounded. So this is exact opposite statement of the third one. So this is wrong. Only correct option here is the third option. Next question. Which of the following statements is or are false? Fiat-Shamit transform is used to transform a public key identification scheme to a digital signature scheme. The signature scheme obtained from Fiat-Shamit transform is secure in random oracle model. In a signature scheme obtained from Fiat-Shamit transform, the signature of a message M has the form R, S, which is a valid instance of challenge response with respect to the identification scheme. Identification scheme is non-interactive, whereas signature scheme is interactive. Okay, I will pause for some time. So they are very trivial questions actually. You can answer. I'll pause for a minute. Okay, so the first statement says that Fiat-Shamit transform is used to transform an identity. So, as you already know that any identification scheme can be converted to digital signature scheme using Fiat-Shamit transform. So as I already said that identification scheme is an interactive protocol, whereas digital signature scheme is non-interactive protocol. And Fiat-Shamit transform works in such a way that the prover basically, or we should say the signer in the digital signature scheme basically runs one instance of identification protocol to generate a valid transcript of identification protocol on its own. So to generate a valid transcript of identification protocol, so what are there in the transcript of identification protocol? If you remember, identification protocol consists of commit, challenge, and response. So all these three things have to be generated by the signer in digital signature scheme, and for that the signer actually itself imitates the role of a verifier in identification scheme for generating a random challenge. Okay, so basically in the game of digital signature scheme, the signer first generates a commitment itself. So remember, in the identification scheme, the commitment had to be sent from the prover to verifier. Now, all the instance of identification protocol is going on in the signer side only. So signer has to sign some message M. For that, first it generates some commitment, but let's denote the commitment as I. Now, commitment need not be sent to anywhere else. It gives the commitment to itself now. So it generates the commitment I. Now, using this commitment I and the message that it has to sign, it applies some hash function h to it. So h of I comma m is computed, and we denote the output as the challenge R. So basically, in case of non-interactive digital signature scheme, the signer does not indeed have access to some verifier kind of thing which was there in the identification scheme. So here, the signer has to imitate the role of a verifier itself. So verifier's job was that to sample a uniform random challenge from the challenge set. That was the case of identification scheme. Now, what if the signer here is corrupted and it chooses some challenge of its own choice? That thing is prevented by taking into account a hash function. So this hash function should be modeled as a random oracle. So hash function takes as input the commitment I and the message M, and it outputs the challenge R. Okay. Now R is because the hash function is modeled as random oracle. This response, this challenge R is actually equivalent to uniformly randomly selected challenge from challenge set. So now using this R, the signer actually computes its corresponding response S by using its own secret key. So we denote the response as S. Now, finally, what signature it generates is of the form R, S, and it sends M the message and R, S the signature to some other party available. So whoever it wants to send its own message and corresponding signature. So for message M, R, S is the signature, and this whole R, S, all these things were generated on the signer side only. There is no verifier as it was there in the identification protocol. So now it becomes non-interactive, and M, R, S is available publicly. Any verifier now comes and tries to verify the signature of message M. What it will do is that it will basically it has the access to R and S, right? So using the verification key and the verifier algorithm, it can compute the value of I just similar to the identification algorithm. Identification scheme. So in identification scheme, the verifier would compute the commitment I by doing the verification algorithm with the verification key, right? Here also same thing happens. It computes the value of the commitment I, but the value of I is not available to it publicly. So it cannot directly match the value of the output of verification algorithm with the value of commitment. So what remaining thing it has to done as extra step in case of signature scheme is that it has to apply the publicly available hash function on the I that is computed from the verification algorithm and the message M that is available to it, and it gets the output R. And now the value of R can be matched with the first component of signature, which is R also. So this R value is actually matched, and if it is matched, then the signature is verified successfully. So that is how a identification scheme, an identification scheme can be converted to digital signature scheme. by using fiat semi transformation. Now, so first statement is of course correct. I just wanted to recapitulate the how fiat semi transformation works. So I described. So second statement says that the signature scheme obtained from fiat semi transform is secured in random oracle model. Yes, it is secure in random oracle model because if it would not be the random oracle, so the hash function is modeled as random oracle, right? Hash function takes as input the commitment value I and the message M that for which the signature needs to be generated. And the output of hash function, because hash function is modeled as random oracle, it appears to be random. And because the signature scheme is not interactive and there is no such verifier existing in this scheme, like the way it was in case of identification scheme. So the signer has to imitate the role of verifier itself and the signer cannot cheat. So to ensure that signer does not cheat in choosing the challenge, it applies the hash function on the message M and the commitment I, and the output of the hash function being random, it is equivalent to choosing some random challenge from the challenge set. Okay, so it is required that the hash function is modeled as random oracle, otherwise the signer could cheat. Okay, in the third statement it says that in a signature scheme obtained from fiat semi transform, the signature of a message M has the form R, S, which is a valid instance of challenge response with respect to the identification scheme. So this is correct. Basically, it describes one step of the signature scheme only. So where if we need to compute signature of some message M, then we basically compute the signature of the form R, S, and R, S is indeed a valid instance of challenge response with respect to the underlying identification scheme on which we are actually applying the fiat semi transform. So this statement is indeed true. And fourth statement says that identification scheme is non-interactive, whereas signature scheme is interactive. So is this statement correct? If you would like to answer. I have already repeated this thing. So if you would like to answer. Is the statement correct that identification scheme is non-interactive, whereas signature scheme is interactive? Okay, so identification scheme is actually interactive. So identification scheme has this commitment, challenge, response, all these things going on between prover and the verifier. But in case of signature scheme, all these commitment, challenge, response, all these things are uh, closed in the signer side only. The signer itself imitates the role of both prover and verifier and finally come up with this whole R, S thing. Okay. So signature scheme is non-interactive and identification scheme is interactive. So this is reverse actually. Last statement is wrong. So the only false statement here is the fourth statement. Identification scheme is interactive, whereas signature scheme is non-interactive actually. Next question. Select the correct statements. In SNOD identification scheme, the commitment has the form I equal to g to the power k for some random k belonging to zq chosen by the prover, such that g comma like capital G comma small g comma q is publicly available group description. So if you remember how like we talked about identification scheme in general consisting of commit, challenge and response phase. commit going from prover to verifier, challenge coming from verifier to prover, and then response going from prover to verifier, and verifier verifies whether the response is indeed a valid response corresponding to the challenge chosen by the verifier. So in a particular instantiation of identification scheme that we call SNOR identification scheme, we take help of this our group structure. So group G is cyclic group of prime order, and small g is the generator of the group, Q being the size of the group, which are any publicly available group description. And actually there is also a public key available, which is of the form h equal to g to the power x, where x is also secret, right? Now for computing the commitment in the identification phase, in the commitment phase, the commitment I is computed as g to the power k in the SNOR identification scheme, where k is chosen by the prover from the ZQ uniformly randomly, and of course k is kept secret from the verifier. So during the identification scheme is running for commitment, the prover chooses some random element k from ZQ, and it computes g to the power k, where g is the generator of the group, and I equal to g to the power k. This value of commitment I is sent to the verifier, and then the verifier picks up some random challenge R again from ZQ set, and R is sent to the prover. In response, what prover does is that it computes Rx plus K mod Q, right? Now, remember X is the secret key, and its corresponding public key g to the power x, also denoted as H, is available to the verifier. Okay. And R was chosen by the verifier and sent to prover. In response, prover replies the response S as Rx plus K mod Q. Okay. So after this, the verifier actually how it verifies whether S is a valid response to R. So it basically computes g to the power S into I to the power minus into h to the power minus R. Okay. So basically g to the power S is nothing but g to the power Rx plus K, right? Because S is Rx plus K mod Q. That is sent by the prover to verifier as response. So g to the power S means g to the power Rx plus K. With that, if it multiplies h to the power minus R, remember h is nothing but g to the power x. So h to the power minus R is g to the power minus xr. Now g to the power S is g to the power Rx plus K, and h to the power minus R means g to the power minus xr. So xr is cancelled in the exponent of g, and only thing that remains is g to the power k, which is nothing but the commitment I. So if this value g to the power s into h to the power r matches with the commitment I, then the verifier accepts that the prover is indeed the entity which claims to be. Okay. So that is how this SNOR identification scheme works. And first statement is indeed correct, which says that commitment has the form I equal to g to the power k for some randomly chosen k from ZQ space. The second statement says that in SNOR signature scheme, the hash function h, which maps any length of binary string to ZQ, is used in order to simulate the role of a verifier in generating a random challenge. Again, this is true. Just now I discussed that the hash function takes as input the commitment I and the message M, okay, in case of signature scheme, and the output of this hash function should appear to be random so that the output of hash function can be used as a random challenge as if generated by some verifier itself. Okay, but it is actually generated on the signer side of digital signature scheme. The signer actually computes this hash function, but because the hash function is modeled as random oracle, its output is never controlled by the signer. So the signer has no control over the output of this random oracle. So it has to generate response corresponding to this random challenge which appears to be coming from some verifier which is not actually existing. So that is why H needs to be modeled as random oracle, and that is how we we prove the security of our uh, signature scheme, which is obtained by fiat semi transform of some identification scheme. So second statement is also correct. Third statement says improper instantiation of hash function H in Schnorr signature scheme may lead to security vulnerability of the scheme. This is true in general because whenever we talk about any construction in random oracle model, that means that except for the instantiation of hash function, from any other point of any other security point of view, the scheme is secure, but only insecurity that the construction may face is that due to instantiation of hash function, because no real world hash function can probably actually be random. Okay, so after all, hash function is a deterministic function, but still using some particular property, we can have hash function which nearly or almost serves as a random oracle. Okay, so believing in such existence of random oracle, only our constructions in random oracle model are secure, but any improper instantiation of the hash function will lead to security vulnerability of such scheme. Okay, so this is true in general for any construction in random oracle. So basically all the statements here are correct. Proceeding to next problem. Select the incorrect statements. TLS handshaking protocol is used by the two parties to decide upon a set of keys to be used by them for encryption and authentication later. TLS handshaking protocol uses symmetric key cryptography. TLS record layer protocol uses asymmetric key cryptography. All of them. So if you would like to answer, I will pause for a minute. Okay. So uh, so in TLS, there are two uh, phase of interaction. First is handshake and then record layer protocol. So handshake protocol is, as it mentions the first statement, that handshake protocol is used by the two parties to decide upon a set of keys to be generated or to be used by them for encryption and authentication later. Later means in the next phase, which is the record layer protocol. So this is indeed true. So if you recall how handshaking protocol works actually, so there you actually make use of key encapsulation mechanism. So as you have seen in case of key encapsulation mechanism, what happens is that any encapsulation algorithm, it generates the output of the form C, K, where K is some uniformly randomly selected key from the key space of symmetric key from the key space of symmetric key encryption scheme, and C is the corresponding encapsulation using the encapsulation key. So the encapsulation mechanism, any KEM, key encapsulation mechanism, has two keys, right? One is again public key and another is secret key, right? So using public key, the encapsulation is done. So encapsulation is done on some uniformly randomly selected key K. This key is selected from the key space of some symmetric key mechanism, symmetric key encryption scheme, right? This K is selected internally and encapsulation algorithm is applied on key K using the using the public key PK of KEM, okay? And that result is denoted as C, and C is actually communicated to other side, okay, to another. There are two party who wants to agree upon some set of keys, right? So the C is communicated to other side, and that that party having access to the secret key SK of KEM, it can actually decapsulate it and get the underlying symmetric key K. Okay. Now both the parties have knowledge of key K, and both of them actually apply some key derivation function on it to get some master key MK. Okay. So this underlying key K, we can also call it, in case of our handshaking protocol, we also call it pre-master key. Okay. And now this pre-master key is passed through a key derivation function to generate master key MK. And then now note that both the parties having knowledge to this pre-master key MK, with the help of this key encapsulation mechanism, both of them have access to this pre-master key, and both of them are actually applying the same key derivation function individually, and they both get the same master key individually, and then both of them applies same pseudo-random generator on this master key MK and generates 4 keys in total. We denote it as, say, KS, KS dash, and KC, KC dash. So S and C stands for, say, server and client. Okay. Now all these 4 keys are generated on both the sides individually, independent of each other, but both of them have same value because the pre-master key value is same on both sides. Now, why 4 number of keys? Because one key will be for encrypting messages going from server side to client. Let's denote it as KS. The key for server for communicating to client. Okay. So one way key it is. But both of them has the knowledge of KS. So the server who encrypts any message using KS, the client is able to decrypt the message using KS only. And the KS dash is authentication key. So in symmetric key paradigm, you send the tag corresponding to any message in order to ensure authentication, right? You remember MAC. So MAC algorithm generates tag corresponding to any message, and KS dash is that MAC key for communication from server side to client side. And KC and KC dash has similar function for communication from client side to server side. KC is the encryption key from client side to server side, and KC dash is the MAC key from client side to server side. So thus there are total 4 keys which are generated on both the sides individually. Okay, so that is how the handshaking protocol works in a very high level in case of TLS protocol. And once this handshaking protocol is completed, you can see both of them has shared key. Okay, common shared key, and using that common shared key, as I mentioned, that in the later phase, which we call record layer protocol, so there basically symmetric key cryptography can happen using this MAC key and encryption key available to both the sides. So KEM being a public key primitive. So the handshaking protocol actually belongs to public key primitive, where you exchange keys, two parties exchange keys among themselves, and then in record layer protocol, both of them runs symmetric key cryptography only. Okay. So basically all the statements given here are correct. Well, not all the statements. So first statement is correct, as you already understood. Second statement says TLS handshaking protocol uses symmetric key cryptography, which is wrong because handshaking protocol uses KEM, which is asymmetric key primitive. So you need to have the flavor of public key cryptography in order to successfully exchange keys without any prior information shared between the parties. So you need asymmetric or public key cryptography in the handshaking protocol. And after handshaking protocol, when the shared key are there between the parties, then they can make use of them to continue with symmetric key cryptography, which will be lightweight as well. So record layer protocol uses symmetric key cryptography, and handshaking protocol uses asymmetric key cryptography. So second and third statement are wrong. So only okay. So second and third statements are wrong. So proceeding to the next question. Which of the following is or are false about the handshaking protocol of TLS? The handshake protocol outputs two pairs of encryption and authentication key, one for communication from client to server, another for communication from server to client. A key derivation function is used to generate master key from pre-master key. A pseudo-random generator is applied to master key to generate all 4 shared keys and none of them. So anyone would like to answer? Just now I discussed the TLS protocol in brief actually. So anyone would like to answer? Like we just discussed about the TLS handshaking protocol. We talked about the shared keys between the parties, the pre-master key and the master key also. So basically, none of the statements are false here. All of them are true. If this meeting ends, then please join in the same meeting. So anyway, so basically all the statements given here are true. Just now I discussed that handshaking protocol outputs total 4 number of keys. So we can say 2 pair of encryption and authentication key. So 1 pair of encryption and authentication key for the communication from server side to client side, and another pair of encryption and authentication key for communication from client side to server side. And key derivation function is actually applied on the pre-master key. So pre-master key is the key that the other party gets after decapsulating the KEM ciphertext. Okay, so after applying key derivation function on the pre-master key, you get the master key, and then you apply pseudo-random generator PRG on this master key to expand it so that you can get total 4 shared keys for the purposes just mentioned. Okay, so all of them are correct. Next problem, which of the following is or are false? So A congruent to B modulo n and C congruent to D modulo n together imply A plus C congruent to B plus D modulo n. Same statement is repeated for subtraction operation then, that A congruent to B modulo n and C congruent to D modulo n together imply A minus C congruent to B minus D modulo n. Third statement says with the same condition that A is congruent to B modulo n and C is congruent to D modulo n, they together imply A into C congruent to B into D modulo n. And then A congruent to B modulo n and C congruent to D modulo n together imply A by C congruent to B by D modulo n. So similar statement are there that A and B are equivalent to each other in modulo n. Okay. So there is answer chat box. B and D seems false. Okay, you were partially correct actually. So D is false indeed, but B is true. Why? Because basically, if you think of the space Zn, okay, so that is actually indeed additive group, so addition operation is defined there and all the elements in the group Zn are having additive inverse. So subtraction operation is defined on Zn. So when we talk about modulo n operations, so if A and B are congruent to modulo n, congruent to each other modulo n, and C and D are congruent to each other modulo n, then all these addition, subtraction, and multiplication, all these operations are defined like, so let us take an example. So let's say if we take n equal to 10, okay, you take any two numbers, let's say 2 and 22, they are congruent to modulo 10, right? And you take 7 and 17, they are also congruent to modulo 10. So let's say A equal to 2 and B equal to 22, and C equal to 7 and D equal to 17. Now, what is A minus C? A minus C is 2 minus 7 modulo 10, which is minus 5 modulo 10, that we can also write as 5 modulo 10, right? Minus 5 modulo 10 is equivalent to 5 modulo 10. And what is B minus D? B minus D is 22 minus 17, which is again 5 modulo 10. So indeed, you can see that A minus C is congruent to B minus D modulo n. Although this is not a correct way of proving this, because this is just an example where this condition is satisfied, that A minus C is congruent to B minus D modulo n, but you can prove this statement in general for any elements in Zn, with the logic that I said, that Zn is indeed a group with respect to addition operation. So each element's inverse is defined. Any element you take, C or D, its additive inverse, that is minus C and minus D, are defined, and this condition is indeed satisfied. But for the option D, as you correctly pointed out, that D will be false actually, because not for each element belonging to Zn the inverse operation. So when we say A by C, A divided by C, that is actually A into C inverse, where C inverse is the multiplicative inverse of C. And not for all value of n, in general, all the elements of Zn will not have its multiplicative inverse, right? It will have its multiplicative inverse only if this element is co-prime to the value n. Okay. So in general, we cannot say that A by C or A divided by C will be congruent to B divided by D modulo n, because division operation is not necessarily defined for any n. Okay. So that's it. Next question, which of the following is or are false? Again, we have some modular arithmetic statements. So it says A congruent to B modulo n implies A plus K congruent to B plus K modulo n for any K belonging to Z. A congruent to B modulo n implies A minus K congruent to B minus K modulo n for any K belonging to Z. A congruent to B modulo n implies AK congruent to BK modulo n for any K belonging to Z. A congruent to B modulo n implies A divided by K congruent to B divided by K modulo n for any K belonging to Z. And AK congruent to BK modulo n implies A by D congruent to B by D modulo n if D is GCD of K and N. So, which of the statements you think are false among these 5 statements? I will pause for a minute to answer. You want to answer? All correct. No, actually, not all of them are correct. First statement and second statement and third statement, all of them are correct, just with the similar logic as the previous question. So, because addition, subtraction, both of them with respect to the same value K modulo N, if it is applied, then they are correct actually. You can try it on your own. Third statement for multiplication operation also, if you are multiplicating two integer modulo n with the same integer k, then it is true that ak is congruent to bk actually. But then coming to division operation, you cannot always say a divided by k congruent to b divided by k. Why? Because with the same logic that k inverse may not be defined on Zn, okay? Or so with the same logic that not every k in modulo n is invertible, so this division operation may not be defined for every k. So we cannot make this general statement that a divided by k will be congruent to b divided by k modulo n. Now for the fifth statement, ak congruent to bk modulo n implies a divided by d congruent to b divided by d modulo n, where d is GCD of k and n. So like in general arithmetic, we do that whenever there is ak equal to bk, we cancel out k from both the sides and we get a equal to b. But same rule is not applicable to modulo n space, where we cannot say that ak congruent to bk modulo n, we cannot cancel out k inverse from both sides always, because it is possible only if you have GCD of these values k and n as d, then you can actually write a divided by d, because d will be actually having this inverse defined modulo n. So a divided by d will actually be congruent to b divided by d mod n. Okay. So basically here only false statement is the fourth statement. Proceeding to the next problem. Select the correct statements. Square and multiply algorithm is a polytime algorithm to compute modular exponentiation. AKS algorithm is a deterministic polytime algorithm to test primality of an arbitrary large number. Extended GCD algorithm can be useful to compute multiplicative inverse modulo n. All of the above. You want to answer? I will pause for some time. One and three is correct. Yes, they are correct. Even two is also correct. Okay. So square and multiply algorithm is an efficient polytime algorithm actually to compute modular exponentiation. You were correct. So just to recall that if you need to compute modular exponentiation, what you can do basically is that, let's say you have to compute a to the power x. Now you get the binary representation of x, and for whichever bit position x is 1, for them you actually so basically you iterate over all the bits of x from right to left, and for each iteration you just compute square of the value a, right? You are computing a to the power x. So starting from right to left, you will have the values a to the power 0. Then for the next position, you will have a square, then a to the power 4, and so on. So for each iteration of the loop, actually, you will compute square of the previous multiplier, and the multiplier will indeed be multiplied to the accumulator. So the initial variable where you are storing or updating the final computed value, so that will be updated in each loop whenever the bit position is 1. So the multiplier will be squared. The name of the algorithm is square and multiply. So square operation will be performed each iteration of the in each iteration of the loop, but the multiplication algorithm will be done only when the bit value of x in the binary representation of x, the bit position is 1, then only that corresponding multiplier value will be multiplied. and that's how square multiply algorithm works. And this is indeed a polytime algorithm, polytime with respect to the bit length of the input. Okay. Now, next statement, AKS algorithm is a deterministic polytime algorithm to test primality of an arbitrary large number. This is true. Before AKS algorithm, there were several primality testing algorithm, but all of them were actually probabilistic algorithm. There were yes biased algorithm or no biased algorithm. So by biased algorithm, we mean that if your algorithm uh, outputs in positive, so the question we try to answer to the algorithm is that is n a prime number? Now, if you get the answer as yes, so there could be some case, in case of no biased algorithm, there could be some case that when it answers yes, so there can be actually some case where the answer is actually no. That means that maybe the number is actually composite, but the algorithm will output the answer as yes, it is a prime. So that is wrong. But if the algorithm answer as no, that it says that the number n is not a prime, then it is always correct. So whenever it gives answer in no, so that answer will always be correct or correct with 100% probability. But the if it answer is yes, that is it says that the number is prime, then with very small probability there could be the case that the number is not actually prime, it is composite, but the case was missed by the probabilistic algorithm. So these kind of algorithms used to exist previously before AKS algorithm, but AKS algorithm is one polytime algorithm which is deterministic. So there is no randomness involved in the algorithm. It is indeed deterministic algorithm, and with 100% correctness, it can determine the primality of a given large number. So the statement is correct. Third statement, extended GCD algorithm can be useful to compute multiplicative inverse modulo n. This is also true. By Bezout's relation, if you have D as GCD of two number A and P, then Bezout's relation says that you can write D in the form of UA plus VB, where both U and V are integer. So you are computing GCD of two numbers A and B. Then if you compute the GCD of A and B as T, then you can of course write D as in the form of UA plus VB. That is what Bezout's relation says. And there is this extended GCD algorithm where you follow the Euclidean GCD method, but in each iteration you also try to maintain two other variables of the form U dash and V dash, and by maintaining this U and V value of each step, you can at the end of extended GCD algorithm, you come up with this exact value of U and V. Okay, now in case of computing inverse, what happens is that you already know that what do we mean by inverse? That is, AB should be congruent to 1 modulo n, right? That is when we say that A is multiplicative inverse of B or B is multiplicative inverse of A, right? So in that case, if you compute GCD of A with respect to some value n such that A and n are co-prime to each other, okay, so you take some n such that A and n are co-prime to each other, and then you try to apply extended GCD algorithm on A and n. So you are trying to compute GCD of A and n. Okay, so you will ultimately get an answer of like you will ultimately get the GCD as 1 because they are co-prime to each other. That is known. But this 1 can be represented in the form UA plus VN, okay, by Bezout's relation while doing the extended GCD algorithm. Now, once you got 1 equal to UA plus VN for some UV in the integer space, then you apply mod n to both sides. So 1 mod n gives 1, and that is congruent to UA mod n plus Vn mod n. And because Vn is multiple of n, so that means Vn is congruent to 0 modulo n. So finally you get 1 congruent to UA modulo n, and your U is nothing but actually multiplicative inverse of A. That is how extended GCD algorithm works. So to compute multiplicative inverse of some integer A in Zn place, you actually can make use of this extended GCD algorithm to compute the multiplicative inverse. So the third statement is correct. Next problem. Assume B wants to verify A's identity depending on the fact that only A has legitimate access to some confidential information. B wants to verify if A indeed has it. So which statement is or are wrong? So there are some statements given. In zero knowledge proof paradigm, authentic A is able to prove to B that it indeed has the access without disclosing anything about the confidential information to B. Zero knowledge proof technique ensures that B cannot present itself as A to some other verifier C using the proof information received from A. A zero knowledge proof system for specific problem consists of 3 algorithms, all of the above. Which of the statements are wrong? I'll pause for some time, you can answer. Okay, so you would like to answer? So when we talk about basically zero knowledge proof paradigm, then what do we mean by zero knowledge proof basically? So in general, whenever we give proof to some particular claim, so usually the verifier has access to the whole proof, right? So in physical world, you go through line by line statement of the proof, and finally you are convinced that okay, whatever claim it was there initially by the proof argument, the verifier is convinced. Okay, but in our scenario, we actually want to, so there is two entity A and B, and A has access to some confidential information. Now there may be the case that there is some adversarial entity A dash who wants to claim falsely that it has access to that confidential information, and B is some verifier who is verifying the identity of A dash. Okay, so it wants to know whether A dash who is claiming to have access to this confidential information, whether it is indeed that entity of that designation to have the access to confidential information or not. So B wants to verify. But the point is here in our scenario, if as a proof A or A dash, so A dash does not, so there is basically two scenario. One is that verifier is corrupted, another is that prover is corrupted. So if prover is corrupted, that is the case when A dash comes in and claims that it has access to confidential information falsely. that is the case where we say that the prover is dishonest and the verifier is honest, but such a prover should not be able to claim itself to be a valid entity with the help of the fact, like with the help of this structure of our zero knowledge proof, and it should not be able to prove correctly. Okay, so verifier may ask for some response to some challenge, and it should not be able to respond in proper way if it is an imposter. But there can be case where the verifier is corrupted. Then what happens is that the prover, if it discloses the part of confidential information to show it as a proof that look, I have indeed access to the confidential information, then the verifier make use of that confidential information itself. So the prover does not trust the verifier, but prover has to prove that it indeed has access to the confidential information without leaking any data about the confidential information. That is where zero knowledge proof comes in. And so the statement here says that in zero knowledge proof paradigm, authentic A is able to prove to B that it indeed has the access without disclosing anything about the confidential information to B. So that is what the whole purpose of zero knowledge proof. So first statement is correct. Second statement says that zero knowledge proof technique ensures that B cannot present itself as A to some other verifier C using the proof information received from A. So that is what I was just saying, that after B verifies A to be an authenticated entity, if it gets some information from A, which it can reuse for its own purpose. If it is B is corrupted, so for its own purpose, it can use that information and verify itself to be an authenticated entity to some other verifier C. So that should not be the desired scenario. So second statement is correct, that zero knowledge proof technique actually ensures that such thing does not happen. Third statement says that zero knowledge proof system for specific problem consists of 3 algorithms. So this is wrong actually, because zero knowledge proof system consists of 2 algorithms. Okay, so one is proving algorithm and other is verifying algorithm. So that is it. So the zero knowledge proof system is defined with respect to some particular relation or problem where you have some claim and you will have some witness to that claim, but you cannot disclose the witness in raw form to the verifier. So you make use of some particular technique. One is proving technique and there is algorithm for verified algorithms. So only 2 algorithms are there, not 3. So third statement is wrong here. Coming to next question, which of the following is or are desirable features of zero knowledge proof system? Completeness, soundness, zero knowledge, all of them. Maybe you would like to answer this straightforward question. Which are the desirable properties of zero knowledge proof system? Okay, so basically all of these 3 properties are desired from zero knowledge proof system. First one is completeness. This is nothing but the correctness of zero knowledge proof system, which says that in case both the prover and verifier are honest, so they are just running a defined protocol without doing any malicious things. So then if an honest prover comes up with some particular witness, then with that witness, the verifier actually should be able to uh, like the verifier should be convinced that the prover is indeed having access to some information, right? So the if the prover is honest, then an honest verifier also should be convinced with the witness it produces. That is the completeness property. And soundness property says that in case the prover is corrupt, so it come up with some falsely generated witness, then that witness should not be treated as a valid witness to the claim. So the verifier should reject that witness. Okay, that is what is the soundness property, defining the case for honest verifier and corrupt prover. And the zero knowledge property comes to play where the prover is honest but verifier is corrupted. So we want to ensure that verifier does not get any information leaked from the prover side about the secret information that the prover has. So that is zero knowledge property. So all of them are correct, basically. So just now I discussed this, so you can answer this yourself by this. You would like to answer the matching? So I just discussed that the honest prover, honest verifier case is uh, taken care of by the completeness property of zero knowledge protocol. Then honest prover, dishonest verifier. This case is taken care of by the zero knowledge property of the zero knowledge proof system. And then dishonest prover, honest verifier. This case is taken care of by the soundness property of the zero knowledge proof system. The last question, select the correct statement. In a zero knowledge proof for graph isomorphism, a prover can cheat the verifier with probability half in a single round of interaction. In a zero knowledge proof for graph isomorphism, a prover can cheat the verifier with probability 1 by 2 to the power k after k rounds of interaction. And multi-party secure computation uses zero knowledge proof system. All of the above. Would like to answer this? Okay. So basically, all of the statements are correct here actually. So in zero knowledge proof, uh, so like whenever a prover tries to cheat the verifier, basically your zero knowledge protocol can be like this interaction between prover and verifier can go on for k number of times, and the probability that the uh, prover, if it is not a valid prover, if it is actually a cheater, then it will be able to cheat the verifier in all these k number of rounds, that is only 1 by 2 to the power k. Or in other words, in any one single round of interaction, independent of other rounds, in any individual single round of interaction between prover and verifier, the prover is able to come up with the correct response to the verifier. That probability is exactly half. Okay. So for graph isomorphism case, if you remember, so the problem is that given two graphs, say G1 and G2, this prover actually knows that these two graphs are isomorphic to each other. But how do it prove that it indeed knows the bijection between these two isomorphic graphs? Okay, so it cannot disclose the bijection itself to the verifier, because in that case verifier will also have the information of the bijection, and it can have access to this confidential information and can misuse it to claim itself to be the entity that prover actually is. Okay, so bijection cannot be disclosed to the verifier. So what the prover can do is that it basically comes up with a third graph H by applying some other bijection to one of these element graph. So let's say it creates a bijection on G2. Okay, this bijection is different from the bijection existing between G1 and G2 that the prover already knows. But it comes up with some other bijection, one-to-one onto mapping from graph G2 to obtain another third graph H. Okay, now it actually sends this it then sends this information like this graph H to the verifier, and verifier asks for bijection either from G1 or from G2. So if the verifier asks for a bijection from G1 to H, then Alice actually compose the two bijection, the bijection that is there from G1 to G2. With it, it composed the bijection that it later created from G2 to H. And composing these two bijection, whatever bijection it gets, it responds that bijection to the verifier. And verifier actually, if it indeed the prover is indeed has information of the bijection between G1 to G2, then it is able to come up with the correct bijection. And the verifier is convinced that yes, that bijection is indeed from G1 to H. And if the verifier asks for bijection from G2 to H, then the bijection that the prover selected, it can give that only to the verifier. But in both these two cases, nowhere the actual bijection from G1 to G2 is disclosed to the verifier, but verifier is able to verify that the prover has indeed access to the bijection G1 to G2. Otherwise, it would not be able to come up with the correct bijection from G1 to H, right? So this, or if the prover tries to cheat here, then at each round, it has probability to randomly come up with the correct bijection. So basically, it has to guess beforehand that whether the verifier is going to ask for the bijection from from G1 to H or from G2 to H. That it has to guess beforehand, and accordingly it sends the bijection to verifier. Okay, but this random guess probability is nothing but half. So at each round of interaction between prover and verifier, the probability that the corrupt prover is able to cheat the verifier is exactly half. But if you repeat the same interaction with various other values of H and the second bijection, then each time the prover is able to cheat the verifier, that probability is very small, that is 1 by 2 to the power k. And any one round, if the prover fails to correctly come up with the correct response, then only the verifier aborts and rejects the prover. Okay, so any one round the prover is not able to cheat, then it is not going to prove itself to be the entity. So by repetitive application of this interaction between prover and verifier, the verifier can be convinced that the prover is indeed having information about the bijection from G1 to G2. So that is how it works. So the first two statements are correct, and the third statement is multi-party secure computation uses zero knowledge proof system. This is also correct. So multi-party secure computation in itself is another vast topic, but yes, they use zero knowledge proof system in order to verify each other's identity. So all these statements are correct here. So that is it for today. In the next week, actually, I will try because you had only 12 weeks of course in this foundation of cryptography course is 12 weeks course, and because we have covered all the topics of these 12 weeks already, so there will be another tutorial session next week, that is 22nd April, Saturday at the same time. But on that day I will try to get an overall brief of the course content overall. Okay, so I will try to just briefly go through all the materials that have been covered in the last 11 weeks. Okay. So that is it for today. If you have any question, you can ask, or otherwise I will end the meeting. Okay. Bye. Thank you for joining.